We will start our problem with a right-angled triangle with the hypotenuse of 5. And we will pull the height of this triangle from its apex, and in this way we will divide it into two right-angled triangles. Let's say that the left triangle has the area of 1. The question is, what is the area of the right triangle? This problem was sent to me by my subscriber Jerry, and I have to say this is a wonderful problem. It looks quite simple, but it actually requires a lot of different techniques to solve. So, if you guys want to try it out for yourself, you can pause the video as always and then come back and check the solution. Alright, so let's solve this one together. Before we start, I am going to label all the vertices of our triangle as A, B, and C, and I will label the remaining intersection point as D. Now, let's take a look at the right-angle triangle ADC. Let's label the height of this triangle as h and the base as x. Now, we all know that the area of the right-angle triangle equals to the half of the product of the base and the height, or x times h over 2 in our case. And we know that the area of this triangle is 1, so we have our first equation. We can first multiply by 2 and get the following, and from this we will get that h equals 2 over x. And we're going to save this equation for later. Now let's have a look at the segment DB. This segment actually represents the difference between the hypotenuse AB and the base of the triangle on the left, x. So this segment must have the length of 5 minus x. This segment also represents the base of our wanted triangle DBC. Alright, so since the triangle ABC is a right-angled triangle, we can use the Geometric Mean Theorem. This theorem only applies to right-angled triangle, and if we pull a height of this right-angled triangle, we will divide its hypotenuse into two segments of P and Q. If this is the case, then this theorem states that the square of the altitude, or the height, is equal to the product of two segments into which it divides the hypotenuse. And this is perfect for our case on the left. As you can see, we can use this theorem and say that h squared equals to the product of the segments x and 5 minus x. Great. So now, we can just use this equation and substitute the value of h and get the following. Now we can work through this, and we can multiply both sides with x squared because we know that x is the length and it cannot have the value of 0. Therefore, we will get the following, and we will put all our terms on the left, and we're going to be left with this really nice but a little bit terrifying polynomial equation. Now, there are multiple ways to solve this equation, but here I'm going to use something that is called the factor theorem, or maybe you have heard the term the little Bezout theorem. So, the factor theorem establishes that x minus c is a factor of the polynomial of x if and only if the polynomial of c equals 0. Great, but how to find the value of c for our polynomial? Actually, the value of c can be usually found by using the factors of the last term of our polynomial, which in our case is 4. We're going to start implementing the factors of 4 into our polynomial and hope to have the results of 0. So, the factors of 4 are 1, 2, 4, and of course their negative values as well. So we're going to start with the value of 1. We will implement the value of 1 instead of x into our polynomial. If we do this and calculate, we will get 0. So this means that we're lucky, and it also means that x minus 1 is the factor of our polynomial. which means that if we divide our polynomial with x minus 1, it will have the remainder of 0. So in this way we have the first solution of our polynomial, that x equals 1. Alright, but as I said, this is only one solution, and we need to check if there are any other solutions, because as you can see, our polynomial is to the power of 4, so there can easily be other solutions. You can solve this in multiple ways. You can use the polynomial remainder theorem or the Bezout's theorem, and you can factorize this, but to be honest with you, I'm going to use a little bit of a different, let's say, geometrical approach to see if there are any other positive real solutions for x. So how are we going to do this? Well, we're going to take a look at our triangle ABC on the left. Since this is the right angle triangle, this means that this triangle represents the half of the rectangle. So we can circumscribe the circle around this triangle. Or in our case, I will use just a half circle, because AB must be the diameter of this half circle. And if you don't know why this applies, or you need a proof, well, the actual proof is quite simple. If we put the point O at the center of the line AB, then the angle AOB will be 180-degree angle. So we can use the Inscribed Angle Theorem to prove our previous statement. Inscribed Angle Theorem states that an inscribed angle inside any circle is always the half of the central angle that subtends the same arc. If I label the sketch on the right the same as sketch on the left, you can clearly see that the angle at the point C is a 90-degree angle, and this is an inscribed angle, and the angle at the point O will be the central angle. Since the angle at the point O is twice bigger than the angle at the point C, this means that the circle can be circumscribed around this triangle. Alright, so now let's see how should we approach this. First, we know that the value of h times x must be equal to. This means that if we increase the value of h, we must decrease the value of x in order to retain the same product. This also applies vice versa. Now, we're going to use this fact to try to find the other solutions for x. But we're only going to use the half of our semicircle. Why? Well, because the symmetry applies on the other side of the circle for the same triangle, so it doesn't make any sense to go any further. This actually means that the x must have the values in between 0 and 2.5, since the diameter of our circle equals 5. And we will write down those values on our sketch as well, so you can graphically see what's going on. Now let's say that this value on the sketch for x equals 1, and we're going to investigate two possible scenarios. First, we're going to investigate if there are any solutions for x in between 0 and 1. And on our sketch, we're going to go to the left of our point. So first we will slide our point to the left, somewhere, it doesn't matter where, and we're going to conclude that the value for x for this point is lesser than 1. But what happens to the height? Well, actually the height for this point is also lesser than h. So, since h decreases and x decreases as well, this means that there are no possible solutions in this interval. Why? Because as we said before, x times h must have the value of 2. So, if we decrease both values, this will not be possible. Now, let's take a look at the other scenario, where x is in between 1 and 2.5. So we will slide our point to the right somewhere, and we can conclude that this value which we got is greater than 1. But what happens to the height? Well, as you can see, the height also increases. So, since both values for x and h increased, there is no way that their product can remain 2. So, this means that there are no possible solutions for this scenario as well. So, this will lead us to conclude that the only possible solution for x is that x equals 1. Alright, so now, with this in mind, we're going to combine our two equations, or we're going to implement x into h, and we will get that h equals 2. Now, remember, we're looking for the area of our red triangle DBC, and this is the right angle triangle, so its area will be equal to the half of the product of its base DB and its height DC. So, if we substitute the values from our sketch, we will get the following. Now we will just substitute the values for h and x, and we're going to cancel out 2, and we will get that our wanted area equals 4, and this is our solution. So I really hope you enjoyed this really interesting problem. If you did, do not hesitate to leave a like or subscribe to the channel for more content like this. Also, if you found another way to solve this problem, please write it down in the comment section. And as always, until next time, see you guys and take care.